Axioms of tile models. We have discussed many examples of tile models. To make derivations about tile models, we need axioms which describe what kind of structures the tile models are. Every tile model has order as part of the structure, but in addition we have the colors. So the axioms of tile models have to include the axioms of order and in addition some extra axioms about the colors. Again, it's useful to think of a person or a computer who has never heard word tile and cannot make sense of our pictures for whatever reason. We use the word tile really in a rather technical sense. It's not a tile which is put on a floor of a building or something, or on the wall. This is a mathematical structure. So these axioms try to describe exactly what is it that we mean by tile models. So the first axiom is that this less than relation is an order, in the sense that we have discussed earlier, which means that tiles are side by side from left to right. The next axiom says that no tile is both red and blue, that the color is in this sense unique. For all x, negation, left parenthesis, bx and rx, right parenthesis. Remember that bx is the predicate x is blue and rx is the predicate x is red. Think of tile models in terms of our axioms, then bx just says nothing. It is just a unary predicate. But this axiom says that the unary predicates b and r are disjoint. No tile is both blue and yellow for all x, negation, left parenthesis, bx and yx, right parenthesis. And finally, no tile is both red and yellow. Then an axiom which says that every tile has a color. Every tile is red, blue or yellow. For all x, left parenthesis, rx or bx or yx, right parenthesis. Of course, all tile models satisfy the tile axioms. And now the idea is that whatever we say in our predicate logic about tile models should follow from these axioms and the axioms of order. Let us look at some examples. These formulas are derivable from the tile axioms, so they represent properties of all tile models. The first says that if x is red and y is blue, then one is left of the other. So for all x, for all y, left parenthesis twice, rx and by, right parenthesis, implies left parenthesis x is less than y or y is less than x, right parenthesis twice. This is derivable. Note that by just the axioms of order, we know that x is less than y or y is less than x or x is equal to y. But that is hardly possible when one is red and the other one is blue. Then, if every red tile is left of x, then x must be blue or yellow. In symbols, for all x, left parenthesis, for all y, left parenthesis, ry implies y less than x, right parenthesis, implies left parenthesis bx or yx, right parenthesis twice. The idea is that if we look at a tile x, and we know that every red tile is strictly left to x, then x cannot be red because then it would be strictly left to itself, which is impossible by the axioms of order. Next, if every red tile is left of every blue tile, then every blue tile is right of every red tile. Well, sounds pretty obvious, but still we need to use the axioms of order and tile models to prove this. In symbols, for all x, for all y, left parenthesis rx and by, right parenthesis, implies x less than y, right parenthesis. Implies, for all x, for all y, left parenthesis twice, bx and ry, right parenthesis, implies y less than x. So this formula is an implication, and the hypothesis says that every red tile is left of every blue tile, and the conclusion says that every blue tile is right of every red tile. It's an easy derivation. In reality, we think of tile models as finite, but we cannot express this in predicate logic. This follows from the so-called compactness theorem, which we have not proved. So we just have to accept that. Even if it would make perfect sense to think of infinite tile models, which would just stretch left and right indefinitely. But that's not what our tile models are like. Axioms of graph theory. Graphs are binary predicates which are antireflexive and symmetric. So we have two axioms. The first axiom, antireflexivity, says for all x, negation x e x. So this says that there is no edge from a vertex to itself by our decision. That would be a different kind of graph if we allowed edges from vertex to vertex, which is quite possible. But we have agreed that our graphs are antireflexive, so we write as an axiom of graph theory the antireflexivity. The other axiom is symmetry axiom. For all x, for all y, x e y implies y e x. So if there is an edge from x to y, then there is an edge from y to x. So our edges, the lines in the pictures of graphs, don't have arrows. We could consider also lines with arrows. That would be like a directed graph. But that's not what we mean here. Here, by a graph, we mean one which is symmetric. So these are the two axioms of graph theory. Of course, all graphs satisfy the graph axioms virtually by definition. Now we can draw some conclusions from the graph axioms. So these are properties that hold in every graph, but we can actually prove them by natural deduction from the graph axioms. The first says, some node is the neighbor of every other node, but in two different ways. That's why this first property is an equivalence. In symbols, exists x for all y, negation y equals x implies y ex, if and only if exists x for all y, negation x equals y implies x ey. So really, the left side and the right hand side both say that some element x is a neighbor of every other node in two different ways. This equivalence says any two distinct nodes are neighbors in two different ways. For all x, for all y, y is not equal to x implies y ex. If and only if for all x, for all y, x is not equal to y implies x ey. Finally, we have the axiom of antireflexivity in an equivalent form. For all x, for all y, x ey implies not x equals y. So these are all rather obvious properties of graphs, and they are here simply as exercises of something that we could try to derive using natural deduction.